So for the graph given here, we want to explain why it has at least one Euler circuit and then define one possible example. And to do this, where I've already copied down a picture here because I'm going to be doing some erasing and rewriting and I don't want to deal with recoding all of those examples, unfortunately it means you're going to be relying a little bit on my artistic skill that happens, and hopefully it'll engender me a little bit more to you. It's not super important if your picture's perfect here, you just got to know what you're doing roughly. But as we can see here, all of our vertices are going to have even degree. As we can see, you've got degree 4, degree 4, degree 4, degree 4, degree 4, and degree 6. So we have ourselves some Eulerian circuits, which I'm going to abbreviate E circuits here. And the thing about Eulerian circuits, the thing about being able to find and define potential Euler circuits with these kinds of graphs is that, technically speaking, we don't just have the one. And we actually have a whole bunch of different ways that we can define an Eulerian circuit. For example, one way that we could end up with one would look something like this picture here, where we can see the pattern of edges selected here like so, but there's actually no reason why we have to follow that specific pattern there, or even that convention with arrows and numbers. In this case, I'm going to go a little bit closer to the notation we'll see later on there, and I'm going to pick a different sort of path. I'm going to pick a slightly different arrangement for how we can follow through on these things using a bit of what we might call the brute force method for being able to find this stuff. We're just going to work our way through it as best we can without doing anything too systematic. But what we're going to do here, at least for me, is figure out where we want to start from. And usually, because we want to avoid making any bridges, we want to avoid causing problems, we're not going to be able to get back to something and abandon some edges on the outside by themselves, is we're going to start from the vertex with the largest degree and work our way outwards, where for this, for no good reason at all, I'm going to pick this edge here in particular as my place to start. So that's going to be number 1. And then what I'm going to do is come over to here to B, and I'm going to come around the outside out here to C, just because it feels a little bit nicer here to go around the outside, as it were, instead of the inside. And then I'm going to just keep looping around the outside, just to keep doing so. Also here, because I want to be careful about making sure I don't get to these for a little while, because if I cut either one of them off, it's going to be hard to get to the other. Anyway, here, I'm going to make this bottom one the third edge that we're going to travel through. And then from there, actually, instead of continuing along the outside, I don't want to get myself stuck out here. This guy's already only got 3 left, but this one still has 5. So it might be a good idea instead to come back up to E and get this one, which means, again, this is going to be an important edge to hold on to for a little while because we're running out of space for it. But this is the 4th we're going to take. And then for the 5th, I'm going to follow a path very similar to the one in the example just to be safe here because it is easy to mess this up. We're going to jump out here, take that guy as our 5th. And I just want to say here, just to take a pause, this is kind of the stuff that I like personally for doing graph theory. It's kind of a weird process, but there's sort of an element of fun to it. Like it's solving a kind of odd puzzle for being able to figure out how to progress through this sort of system. This is what draws a lot of people to graph theory, where the things we learned in 14.1 to keep the idea of games in mind are a bit like learning what cards you have in a set or in a deck. This is like learning the rules of a game you can play with them. Where here our game is making sure we touch them all on the way through. Anyway, we are at that 5th one there. So next I'm actually going to come back down here and I'm going to end up clearing out vertex D, which might be a bit of a risk, but that's okay. We'll see why later. So that one's 6. This is all we've got left, which means this one has to be 7 because we've already touched all of the rest of those, and that means the vertex D down here we're never going to be able to visit again, but hopefully we won't need to. But that also means we're going to have to clear out F up here too, coming up to A. So now, essentially, this whole section of the graph down here is finished, which means we are left with just this group of vertices here. This 1, 2, 3, 4, 5 that we have to hit each of exactly one time. And actually, there are quite a few ways we can go about this depending on where we want to start and where we might have in mind to end. But just for the sake of it, I'm going to go up here. So for my 9th one, I'm going to pass along this top outside edge. And again, like I said, you have to be careful coming back into these two, but here we have a nice little path we can follow. If we make this one the 10th in here, and then this one down here, the 11th, then this double pair, we can pick them in either order we want. I'm going to do the top one first. That's number 12. And our last one, lucky number 13, is this edge. So we are both starting and ending here at E, just like we're supposed to. We are progressing through our system where we began at E, go out to B, and then we are finishing up here by coming from E to A, and then back A into E at the end. Just as we need to, just as we mean to for our circuit. So for our next example, we're going to see how we can do the same sort of thing, but instead, we're going to look at it talking about paths.